Okay? So molecule-to-molecule conversions are very similar to gram, except the only difference is we don't have to use the molar mass, but what do you think we might use instead? Avogadro's number, right? Because we're talking about the number of molecules in a mole, not just the number of grams in a mole. Okay, so we've used this balance formula before, so I'll go ahead and balance it for you. But we're going to look at, if we start with 4.21 times 10 to the 23rd molecules of tin, how many molecules of hydrogen are formed? Okay, so this is very similar process to gram, except we don't have to use the molar mass. We use Avogadro's number instead. Okay, so in our T-chart, we always start by writing what we know, right? We're starting with this many molecules of tin. We want to find out how many molecules of hydrogen gas. Okay, because it says it reacts with hydrofluoric acid, is that going to go into our T-chart anywhere? Is hydrofluoric acid going in our T-chart? No. Right? That doesn't mean anything to us here. Okay. So I'm going to start with what I know. Okay, so my process here is going to go from molecules of tin to moles of tin, then to what? Moles of hydrogen, then to molecules of hydrogen. Okay, so I want to get rid of molecules. That goes on the bottom. And 1 mole. How many molecules are in 1 mole of anything? That's right, 6.022 times 10 to the 23rd. If you don't want to write Avogadro's number every time, there's an abbreviation for Avogadro's number, and it looks like this, Na. Okay, that means Avogadro's number. So you can write that in here if you don't want to write 6.022 times 10 to the 23rd every single time. Okay, if you're more comfortable writing the number, go for it. If you see that, that's what that means. It means Avogadro's number. Okay, so now I'm done with molecules of tin. I'm left with moles of tin. So I want to get rid of moles of tin and go to moles of what? H2, okay? And so from top to bottom here, what's going to go in my T-chart? What numbers? 2 and 1, right? Those are our coefficients from our formula. So if I stopped right now, what unit would I be in? Moles of hydrogen, okay? So now I'm going to finish moles of hydrogen and go to molecules. And Avogadro's number goes there as well. Okay, do you notice now that we have Avogadro's number on the top and the bottom? So what does that mean will happen? They'll cancel. So you don't have to mathematically plug in that into your calculator both times, right? If you're going to multiply by it, then divide by it, there's no reason to put it in your calculator. Okay, so the only thing that you need to really do is take your starting amount and multiply by 2. Important that you keep the total name of the compound the whole time. So you can't just leave off SN or H2 or whatever in your T-chart. Because if you do, you'll find yourself getting confused and you won't know which side needs to be the mole ratio for which or things like that. So when you're doing your T-charts, please, 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 please take the time to actually put in the chemical formula in each one. Okay, I know it takes you like another whole second, but just do it, okay? It will save you headaches when we're trying to figure out where it went wrong, okay? All right, I'm going to give you one more question using this same balance formula. Okay, how many, let's see here. Now you should be able to take this process and apply it to any set of stipulations you're given. So you could start in moles, you could start in grams or molecules, and you could end up in any of those 3 things, and you should be able to do it. Okay, so we're going to find out how many grams... No. Sorry, how many molecules of H2 are formed from 60 grams of hydrofluoric acid? Okay, how many molecules of H2 are formed if we started with 60 grams of hydrofluoric acid? So now we're mixing and matching a little bit. We're going to start with grams and go to molecules. So let's see if we can get that done. Okay, how many of you had that answer? Okay, we'll go over it, but I want to see how many of us got there, okay? So if you got that, that's fine, just chill for a second, okay? All right, so we started with grams. So the first thing that has to get gone in our T-chart, right, has to go diagonal is grams of hydrofluoric acid. Okay, and so what has to go above that in our T-chart? Moles of hydrofluoric acid. Okay, so moles gets the 1. The molar mass of hydrofluoric acid is 20.
Oh, I put 20.
20, okay.
I put 20.
All right. So if we stopped right there, right, we're going to cross out grams. If we stopped right there, we'd be in moles of hydrofluoric acid, which is not what we want. So we need to go from moles of hydrofluoric acid to what? Moles of H2. So we still need Avogadro's number, but it'll be later. Okay, this is a multiple ratio step, so we go 2 to 4. Okay, so if we stopped right here, we'd be in moles of hydrogen gas. Last thing we want to do is go from moles of H2 to molecules. So yes, this is where Avogadro's number would come into play. Okay, so if we do the math, we should get 9.03 times 10 to the 23rd. Yeah? Okay? Yeah, Thomas. Okay, so now our question is, okay, if this many molecules of SN are used, how many moles of H2 are formed? So we're taking a step back now, and we're going to stop at moles. Okay, so we are going to look at double displacement reactions. So what happens in a double displacement reaction? They switch, right? What specifically switches? That's right. The cations of one and the anions of the other will switch places. So in double displacement reactions, we should always be able to predict the products based on the reactants given, right? We're going to be given the reactants, and then we're going to guess its products, right? Predict its products based on the fact that we know it's a double displacement. So this is what it would look like. Sodium nitrate reacts with calcium fluoride, and it will yield so on and so on and so on. So first thing we have to do is take them from word form and put them into chemical formula. So this is chapter 7 coming back. Okay? So if you don't know your polyatomic ions, you need to brush up. Okay? Because remember when I said you'll need them all year long? I wasn't kidding. Okay? So if you don't have periodic table of ions out, you might want to get that out real quick. Okay? Okay, so sodium nitrate. Let's start putting that together. Sodium is what charge? No, sodium is... Sodium's Na. +1. And what's nitrate? NO3 minus 1. So sodium nitrate should fit together perfect, right? Reacts with calcium fluoride. So calcium is a +2 and fluoride is a -1. So how many fluorides do I need? CaF2. Okay, if this is not ringing any bells, you need to brush up a little bit, okay? That's what we're going to work on today a lot. But if this is totally foreign to you, you're going to have to pick up the pace a little bit, okay? So when we predict our products of a double displacement reaction, we know that our cation and our anion are going to form a new compound, and our cation and our anion are going to form a new compound. Okay? Does it matter which order we write our new compounds in? No. But within our compound, we have to make sure we list cation, then anion. So first we'll do sodium fluoride, which is NaF. Right? Why is it not F2? Sodium's +1 and fluoride's -1. So we will balance our equation afterward, but we have to build our compounds so that they are individually have a neutral charge. Okay, calcium nitrate. Calcium is a +2. So how many nitrates do we need? We need 2. Okay. So if I take calcium and nitrate and I build a new compound, calcium is +2, nitrate is -1. So I'd cross those charges down. That's how I got CaNO3 2. Okay, does that part make sense? Now we balance the formula. Okay, so what do we need to do to get it balanced? Which Na? This one? This one? So I've got 2 nitrates, 2 nitrates, 2 fluorines, 2 fluorines, 1 calcium, 1 calcium, 2 sodium, 2 sodium. Very good. Okay? So these are the types of questions that you should expect on your test, right? You will have to build and balance the reaction and do a stoichiometry calculation based on that built reaction. Okay? So just a heads up. Okay? So let's take this balance formula that we just found, and we're going to try a problem with it. Okay, let me copy this so I can get it. Okay, if I start with 83.2 grams of sodium nitrate, how many grams of calcium nitrate can be produced? Okay, again, I'm going to recommend that you write above your formula, right, 83.2 grams, and I want to find out how many grams here. That'll help you point to the correct coefficients, right? Look at the correct ratios. Yep, we're always going to do double displacement. Okay, so first find our reactants. You want me to give you a second to try it on your own?
Yes.
Okay.
What?
Nitrate's a -1. So lithium and nitrate combine fine. Too loud, please. Phosphate and aluminum are both 3s. Okay, so listen. How many of you left yours like this? Al3, PO4, 3. Yeah, we have to reduce those. Yeah, yes, you do have to put Al first. Okay, so that's a great question. We have to put aluminum first because it's the cation and phosphate's the anion. So whenever we build a compound, it always has to go positive, then negative. Okay? So when we combine them, yeah, even though it would look like this, PO4Al, we have to make sure that the cation comes first, then the anion. Okay? Any questions there? This wasn't balanced, so our final balancing of this should look like, what, just that? Is that it? Okay, let's try one last problem here with this set. What mass of aluminum nitrate will it take to produce 311.2 grams of aluminum phosphate? Okay, how do we feel? Great. Okay, that's where we're going to stop for notes for today.